In this video, we are going to look at calculations involving the Kc expression or the equilibrium constant expression. So in the previous video, we learned how to write these expressions, and this is often part of the exam question as well. And then in the next step, it'll ask you to use that Kc expression that you've written in order to solve a problem. Okay, so what types of problems do we get with Kc calculations? So there are two main types. The first one is we're given information about the amounts or the concentrations of the reactants and the products. And from there, we're asked to calculate the value of Kc. So in other words, Kc we know in general is concentration of the products over the concentration of the reactants. And that gives us some constant number. So in that case, this is what we're trying to find. What's the constant number? And we know it's a little bit more complicated than this square brackets products over square brackets reactants, because we also have to take the molar constants or the molar coefficients into account. So you saw how we would often have a to the power of a times b to the power of b, and so on. So I'm not, oh, sorry, b to the power of b. I'm not going to do all that again. If you don't know what I'm on about, you need to watch the other video first, okay? How to write Kc expressions. But once we know how to do that and we write our Kc expression, then we can put our information into this equation and calculate this. That's the first type of calculation. That tends to be the easier one, to be honest. There's a second type then where we are given Kc. So we're given this number as, let's say it's equal to 4, we're told this, and then we need to work out one of these things. So we either need to work out A, we need to work out the concentration of B, or we need to work out, oh, sorry, they wouldn't be A, would they, up there? Sorry, that would be C and D. Apologies, C to the power of C, B to the power of D, because these are the products. So I made a mistake there. It's easy to do it. This is why you have to be really careful. Okay, so d to the power of d, and we've got a to the power of a down here times b to the power of b. Okay, and you're given this, and you're asked to work out one of these. Okay, so you'll have the rest of the information, but you'll need to work out one of them. It could be that one, it could be that one, it could be that one, or it could be that one. Okay, but this is what you're being asked to work out. What's in the equilibrium mixture? Okay. So there are the two types of concentrations. A couple of notes, something really important to note, is that when we're doing the calculations, Kc is always calculated using the concentration in moles per liter. And this is why we use these square brackets, because that means concentration in moles per liter. So no matter how the information is given to you in the question, you must work out the moles per liter to put it into the equation, because that's what square brackets means. Okay, so there may be some extra steps in the exam question where you guys have to do this. Oh, by the way, I should mention at this stage that this really is only for higher level students. Ordinary level students don't have to do this, but they do have to be able to write the Kc expressions from the previous video. They don't have to be able to do calculations with them. So this is higher level content. People who are good at maths are going to love this. People who are average at maths can really do well here if they really work at it. If you're trying to avoid the maths questions, like I always say, it's very hard to completely avoid the maths, but you know, this mightn't be the question for you. Okay. All right. So let's have a look then at yeah. So another thing is also important. Remember to factor in the volume of a reaction vessel. So if you're told that you put 10 moles of A into a container, but that container was 10 liters, then we don't put 10 in for A, because that's a total of 10, but that's in a 10-liter container. So that, of course, will be 10 liters in a 10-liter container is equivalent to 1 mole per 1 liter. So that's what we would have to put in here. Okay, so you just have to be a bit careful. I'm not going to tell you how to convert from moles and to grams. You should know that at this stage, but I am going to give you a structure of how we can answer any of these questions. Okay, so I want you to watch what I'm doing here, and I'm going to take this down as notes in a second. Okay, so for solving equilibrium calculations, okay, sorry, my screen is crashing, so just give me 1 second here now, try and get it back up. Share. Get me 1 second, I get the OneNote back up here. Oh, where was I? Sorry about this. Yeah. Share screen. There we go. Okay. Now, should be back there, I'm hoping. Yeah, so for solving any equilibrium calculation, we're going to use a specific layout. We're going to use something called an ICE table, ICE table. I'm going to show you what that is now, okay? So let's take a general chemical reaction. Let's say we have a reaction between A plus B reversibly reacting to make C plus D. Okay, so A plus B reversibly reacting to make C plus D. All right, we're going to use, like I said, we're going to use a table to lay this out. Now, of course, there's no such thing as A plus B gives C plus D. That's not a real chemical reaction. So you draw a line underneath this, okay? I'm going to turn this into a 3-row table like this. 3 rows like that. And then what I'm going to do is I am going to divide it up 1 column per substance. Okay. Now this over here on the left is underneath. There's no letter here. This is for my labels, I suppose. Okay. So we're going to show you now what ICE means. Okay. So the first letter I goes in the first row here. And what it stands for is it stands for initial concentration. And of course, this has to be in moles per liter. Okay. The initial concentration in moles per liter. That's what I stands for. C. C stands for the change. I'm going to show you what that means when we go and do an example. And E stands for equilibrium concentration. Equilibrium concentration. And again, this has to be in moles per liter. Okay, so what I'm going to do is I'm going to get you to take that down, okay, what an ICE table is. So doing that for me now. Now, all this does, guys, this isn't really part of the calculation, of course. You don't have to do it like this. But for me, this provides a structure which assists and scaffolds your thinking about the calculation. Okay. So generally, we're going to get this information from the question. We usually also get one of this, something down here on this line we get from the question as well. The change we'll have to work out, and then we'll have to work out whatever unknowns there are as well. Okay. So what I'm going to do is we should have paused that and take it down. We're going to go and we're going to see how this applies to a real question now. Okay, so we're going to have a look at an exam question here. So just give me a second till I find where I have it printed here. There we go. Okay, so here is the question from, I think it was 2021, this question that I've got printed here. That was 2022, see it there? This was a 2022 question 7, and it's a whole question on chemical equilibrium, okay? We're not going to focus on all of it now, actually, because we are going to, we're going to just focus on the calculation bit mostly, okay? But let's just have a quick read of it, okay? I'm going to get you guys to just have a read from there to there for me. So pause the video and do that now. Okay, so a couple of things to note, okay? I'm going to highlight a couple of important things here, all right? And that is, it says a researcher mixed 5 moles of carbon monoxide. So that's this one here, the CO, okay? 5 moles of carbon monoxide and 10 moles of hydrogen. Okay, 10 moles of hydrogen. So that's obviously the H2 from the equation up here. Okay, and they did this in a 5-liter container. That's going to be important in a couple of minutes. Okay, a 5-liter container, and equilibrium was reached at a temperature of 250 degrees in the presence of a catalyst. All right, let's have a look at part A. Part A is just straightforward definitions for 8 marks. I'm not doing them with you now because, well, basically, we're not focusing on that right now. We've done the definitions, we've done chemical equilibrium, so that's not what we're doing. Part B is where we're interested in, okay? It says, write an expression for equilibrium constant Kc for this reaction. All right, guys, so you guys should know how to do this already from the previous video. So I'm going to get you guys to pause the video and do that now for me. Okay, so anyone who's stuck, remember, Kc is the concentration of the products. Products always goes in the numerator relative to or compared to concentration of the reactants on the bottom. Okay, so now that I've reminded you that, check yours. Is that how you did it? Okay. Okay, right. So let's have a look then at what we should actually write here. So we should write Kc equals, so our expression here, we're going to take the products. There was only one product. It was CH3OH. So square brackets CH3OH on the top. There's no power because there's no number in front of it. There's no coefficient. Over square brackets CO. And again, there's no power on that. Times square brackets H2 to the power of 2. Okay, so that 2 is coming, it goes as a power here. So that is there, and that was what, how many was that word? 6 marks, I believe. Okay, so a nice easy 6 marks. Should all be able to do that now. All right, so now it's going to ask us to use that. I think it's going to ask us to calculate the Kc. So this time we're trying to find out what number this is. We're trying to find out what's the value of Kc. So this is the more straightforward type of calculation. That's the good news. Okay. Calculate the value of Kc under the conditions described above based on the researcher's report of a 25% conversion of carbon monoxide to methanol at equilibrium. So that's going to be important too. I'm going to underline that, 25% conversion. That's going to be important in our question. All right, so the first thing I'm going to do now is I'm going to write down this reaction for my ice table. So I'm going to write CO plus 2H2 reversibly reacts to make CH3OH. And beside that, I'm going to lay out my ice table. Remember, ICE. Okay. Now, remember then I stood for initial concentration in moles per liter. So I have to figure out what was my initial concentration in moles per liter of the carbon monoxide. Okay, so see here I see I had 5 moles of carbon monoxide, but it was in a 5-liter container. Okay, so 5 moles in 5 liters, you should be able to work out that that's 1 mole in 1 liter, 1 mole per liter. Okay, so again, it's always moles per liter for these concentrations. All right, what about the H2? Well, here I've got 10 moles of hydrogen in a 5-liter container. So 10 moles in a 5-liter container would be 2 moles in a 1-liter container. That's going to be 2 moles per liter. Now, if we think about it, the initial concentration, of course, that means at the start. And at the start of any reaction, we never have any product. Okay, so I have 0 moles per liter of my product. I'll always have 0 moles per liter of product at the beginning of any reaction. Okay, now I told you in an ice table, we divide it up like this, so you can do that if you like, but you saw how, you know, you could have done it without dividing it down the middle, but that's fine, okay? Right, the change is going to be the last line that we're going to be able to fill out. So we're going to leave that alone for a second, the change. Oh, well, it may and it may not actually be the last the last line. We might need to use it in a second, but we'll show you. Another thing that to note is we know how to do our molar ratio. It's 1 mole of H2 to 1 mole of CH3OH. Let's go back over here and see, do we have any more information? We've got our concentration of that. We've got our concentration of that. We know that that's 0. What else can we figure out? Well, the next piece of information we could use is down here. It says here that researcher reported a 25% conversion of carbon monoxide to methanol. 25% conversion. Okay. Now, if you think about it, 25% conversion is 1 mole here would give me 25% conversion. So I'm going to add, this is going to change. It's going to go from 0 and it's going to increase by 0.25 of a mole because we're converting 1 mole here by 25%, which is 0.25. Okay, so our change here is this one is going to increase by 0.25 moles per liter, so plus. And of course, that's going to give me an equilibrium concentration. If I start at 0 and I added 0.25 moles per liter, then I've got 0.25 moles per liter as my equilibrium concentration of CH3OH. Now, this is where the change line comes in and it's very important, okay? We must use the molar ratio to compare the change in these moles per liter compared to the change in this and this moles per liter. Let me show you what I mean by that. First of all, if our reactant is increasing by 0.25 moles per liter, then if our product is increasing, this increased, of course, that means that our reactants are going to decrease because they're going down. There's going to be less of them. Products increases, reactants decreases as the reaction goes on. So because this is a 1-to-1 ratio, if this one went up by 0.25 moles per liter, then this one will go down, so minus 0.25 moles per liter. And there we can see that this is going to end up at 0.75 moles per liter. This other one has a 1-to-2 ratio, 1-to-2 ratio, which means that if this is going up by 0.25, this one will go down by twice that number, so minus 0.5. So now we've got the whole change line worked out, and we've got most of the equilibrium concentrations worked out. We just have this last one to do. So 2 minus 0.5 gives us 1.5 moles per liter of H2 at equilibrium. So what we're saying here is that our equilibrium mixture here is composed of 0.25 moles per liter of methanol, 1.5 moles per liter of hydrogen, and 0.75 moles per liter of CO. Okay, so now what we have to do is calculate Kc. Once we have our ice table filled out, we're going to take our equilibrium expression again, which was Kc equals the equilibrium concentration of CH3OH over the equilibrium concentration of CO times the equilibrium concentration of H2 squared. And I'm just literally taking that from where we did it earlier. And what we're going to do now is we're going to put in our equilibrium concentrations, these values. Okay, so Kc equals, I'm going to substitute in on the top line here, it's going to be 0.25 because that's our equilibrium concentration of CH3OH. So we're just subbing that in there over our equilibrium concentration of CO is 0.75 times our equilibrium concentration of H2 is 1.5, and don't forget, and that has to be squared. So now we're going to get our calculator out and put that in our calculator, and we should get Kc equals to 0.148. We'll put a box around that. That's our final answer for this calculation. So that was a reasonably straightforward one. Okay, there are some that are a little bit more difficult. And as you see here, guys, there is a range in your answer there. So 0.148 to 0.15. Anywhere in that range is going to be an acceptable answer. That just gives you a little bit room for a different rounding that you might have done. Right, guys, I'm going to give you another straightforward-ish one to do now. Okay, I'm going to get you guys to do the next one for me. We're going to have a look at 2021, question 9. Again, this was a relatively straightforward one. Okay, And what I want you guys to do is I want you guys to have a go at this for me now. Okay, so pausing the video and working your way down through this calculation. Pause the video, do that now. Okay, you should have got a Kc equal to 0.103. If you didn't get this, guys, you need to go back and have another look and see what you did wrong. Okay, so pause the video and do that one for me now. All right, in another video, guys, I'm going to show you the other type of calculation, and we're going to have a look at some slightly more complicated ones. But these are the straightforward ones where you just have to get Kc from given values. Okay, so hopefully we managed to work this out, and I'm going to show you how to do this one in class. All right, guys, we'll see you in the next video.